everyone, welcome to this channel. So in this video lecture, we will be discussing about some previous year question answers and which has been asked in CSIR-NET as well as in GATE examination. So let's start with the first one. So the first example is basically on iodolactonization. You have the substrate. This is basically acid group. We have a double bond over here. So in presence of I2 and Ki, so I2 will add in this double bond. Basically, it will be I plus. We'll have a carboxylate. So it will form a carboxylate in presence of the base sodium carbonate. It will abstract this proton. It will form a carboxylate. Now what happens? This O minus will attack over here. It will form a 5-member ring. There's a 5-member lactone ring. It will form. So this will attack over here, and this ring will get open. So this will attack here, and this ring will get opened. So basically, the options in option C, so option C and D will not be the answer, because you can see here none of the options are forming any 5-member lactone. So out of option A and B, we have to choose which one will be the correct answer. So as you know, if this 3-member ring formation takes place from the below phase, so carboxylic acid will attack from the top phase. That means the hydrogen attached over here, will be from the below phase, right? So that means in conclusion, the stereochemistry of the iodine and the stereochemistry of the hydrogen will be same. That means if we say this 3-member ring formation takes place from the below phase, so carboxylic acid will attack from the top phase. So the hydrogen in the junction will be from the in the below side. Okay, so assuming the iodine, this 3-member iodinium ion, this formation takes place from the below phase, assuming it. So if it is below phase, the opening will be from the below side, and this lactonization will be from the top phase. That means this hydrogen's stereochemistry will be from the below phase. So the correct option is option A. This is the correct option. So let's move to the second one. So second one is basically based on our benzene mechanism, as you can see. So basically on benzene mechanism. So for this is benzene mechanism, right? So what happens over here? We have a OMe group over here. We have a Cl over here, right? Sorry, the Cl is in the ortho position, right? So let's change the paint color. So the Cl is in the ortho position like this. Now we are giving a base NaNH2, sodium amide in place of glycer ammonia. So what happens is hydrogen will be abstracted by this amide. It will abstract, will form a negative charge over here. We have a Cl group. As you all know, the Cl is a good leaving group, so it will leave, and we will end up with a benzene substitute, right? So this is our benzene derivative. This is a benzene derivative, right? So now we have two options. Either the NH2 minus can attack here, NH2 minus, it can attack here, as well as the NH2 minus can attack here. So if the NH2 minus attacks over here, so we will end up with negative charge. If it attacks over here, the negative charge will be over here, right? And here we have the OME. And if it attacks over here, if it attacks just ortho to OME, so we will get this one. Now, as you can see, the OME group has a minus I effect, right? It has a minus I effect. So what happens? So the negative charge, which is close to an electron withdrawing group, will be more stable. That means this negative charge is stabilized by the electron withdrawing group. And if the electron withdrawing group is close to negative charge, it can easily stabilize it. So that means this one is our correct intermediate. Okay. So after you work up, you have lighter ammonia. So this negative charge will get protonated. So we'll end up with this hydrogen over here. So basically we are getting meta substituent. So the first option is correct. Right? The first option is correct. So moving on to the next example or next question. Okay. So what is given over here? I have this one. Okay. So basically over here you have an N2. We have a sodium ethoxide that is a base, right? So if we add a sodium ethoxide, what will happen? It can abstract this proton, right? There is no other option to abstract this proton. So it will abstract this proton and we will get a benzyl anion, that is a stable anion. Because this negative charge is stabilized by this phenyl group. Also, it undergoes extended conjugation with this nitro group. So basically this negative charge is stable. It's a stable species, right? Next, what happens? Next, we have OIT, right? So just drawing this, let me not draw like this. And draw. So we have a CO. That means we have a CO and we have a OIT group right here. So this negative charge, what happens? It will attack here. So OIT will leave the system, right? So OIT will leave the system. Basically, we are getting over here, we say CO2, ET, and we have an NO2 group. Now what happens? We have given zinc acid. So this one, what it will do? It will basically reduce NO2 to NH2, right? So reduce NH2, NO2 to NH2. So we'll get this one, NH2. We have square, here we have a CO2, right? Okay. Next, what happens? Next, this one will form a 5-member ring. So basically, this will become a positive. Then this proton will be abstracted over here. There will be shift to proton. Proton will be abstracted over here. This one becomes OH. Then we are getting this one. We are getting over here a CO2 ET, right? And here it's the, okay. Next, what happens? Next, this portion, this hydrogen will be abstracted. That means water elimination takes place. some water elimination text is over here. Basically, we are ending up with an indole derivative, right? So this we are getting a indole derivative. So getting indole derivative. Okay. So this is the product. So this question has been asked in CSIR-NET exam in June 2013, and the same question, full Tito same question, has been repeated in GATE 2020 this time. The same question. They didn't change the options also. The same question has been asked in GATE 2020 also. Okay. So moving to the next one. So this is basically, we have given a benzaldehyde, then TMSCN, zinc catalyst. Okay. So this is basically a type of benzene condensation. It's not a benzene condensation, but it's type of benzene condensation. So what happens over here? We see we have this CH. So we are given a TMSC. What is TMS group? TMS is trimethyl silyl cyanide, right? That means we have Me3SiCN, right? So this is TMSCN. So basically what happens, you have a TMS plus and CN minus, so CN minus will attack and this O minus will abstract this TMS part. Okay, so OTMS, we have a CN, right? Now it's given LDA. The LDA will basically abstract the acidic proton. So this proton will be abstracted. Why this will get abstracted? Because see, after abstraction of proton, we are getting this carbanion, and this carbanion is stable. Why this is stable? Because we have an electron withdrawing group attached to the carbanion. So it is stable, right? In the next step, we have given a isopropyl iodide. So this is a isopropyl iodide. So this will attack the type of SN2. So what we are getting OTMS over here. Here we are getting the isopropyl group. So we have the cyanide. The next step, go to hydrolysis. That means the TMS group will get converted. The TMS group will get converted to OH group, right? It will get converted to OH group. That means we are getting this OH, third, and cyanide. Next, again a base is given, again abstraction of the OH proton. Okay. Now cyanide is a good leaving group, so the driving force, so this O minus will come here, it will form a keto, and the cyanide leaves the system. So basically, we are getting this as a product. So the correct option is option D, right? Next example, this is a very good example, and this is common question, and it's a favorite question for the examiners. Okay, so what happens? So this portion, we have a decalin system, and first we have to draw the chair conformation. If we draw the chair conformation, a very easy question, very easy question. If we draw the chair conformation, it will be very much clear. We have a hydrogen in this junction, and here the OH group is below the plane, and the OTS group is above in the equatorial position, right? Now we have given a KH, right? So what KH does? Basically, KH will abstract this OH proton, right? So it will abstract this OH proton to form a O minus, okay? So basically the O minus. Now see, OTS is a good leaving group, right? OTS is a leaving group. So this carbon OTS bond and this bond should be anti-periplanar, and it is there, it is anti-periplanar. So this O minus will come here, it will form a double bond. This bond will shift and this OTS will leave. Okay. So this makes this is possible as because this OTS bond, this bond, this bond, and this bonds are anti-periplanar. That is why it become possible. So if it leaves the system, so we are ending with this product. So basically, we're ending with this one, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So here we have a keto group, and here we have a trans bond, right? So as you can see, options C and D are not possible because we don't have the OTS system, OTS in the product, and we will not have the OH group in the product. It will form a keto. So in between option A and B, then one of the options will be correct. So as you can see, this is a transform. Okay. So in option A, it is a transform, and in option B, it is a cis form. So as it is a transform, so option A is correct, right? So this is all for this video, and thanks for watching.